Okay, so let's look at the relation between Cp and Cv and see. I told you that this value Cp minus Cv is equal to R, and let's see why this is true. Why is this happening? So here we have two processes. One, this process here is at constant volume, and this process here is at constant pressure. In these two processes, we added heat. Here we added heat and the pressure increased. Here we added heat and the gas expanded. So how much heat did we add? Well, in the first process at constant volume, right? At constant V, then we added Q is equal to the number of moles times Cv times delta T, where delta T is just the difference between the final temperature and the initial temperature. So let's write that here. Delta T is Tf minus Ti. In the second process, this one here, then that process is at constant P. The heat that was added is N Cp times delta T. Okay, so now to prove this relationship up here, we need to use an important fact about ideal gases. The energy E thermal for an ideal gas depends only on the temperature, on T. Okay, in fact, that energy E thermal is equal to the number of moles 3/2. Let me rewrite this. Is equal to 3/2 the number of moles RT. Okay, so that is an important fact. So that means that if I go from an initial temperature, if I go from Ti to Tf, then delta E thermal is the same no matter which process I use to go from I to F. So in these two processes, I went from this initial temperature to this final temperature, which is the same for both final processes, right? Because this is an isotherm. So therefore, delta E E thermal is the same for both processes. And this is the key to understanding this relationship, this fact here, that delta E thermal, the change in the thermal energy of a gas is the same for any two processes that have the same delta T. Okay, this is a line that I'm reading from your book right now on page 525. The change in the thermal energy of a gas is the same for any two processes that have the same delta T. What that means is that for the constant V process, delta E thermal, right? Delta E thermal would be equal to what? Would be equal to the heat plus the work done. And in this case, the work done is zero because it's constant volume, so it's equal to the heat and it's equal to Cv, the number of moles, times delta T. For the constant pressure process, then delta E thermal is equal to what? Is equal to Q plus W. Now this is equal to Q, which is N Cp delta T, right? Plus W. What is the work done? Well, it's an isobaric process, so the work done is just minus P delta V. Okay? So now these two things are equal, right? Because they are going from the same initial temperature to the same final temperature in both cases. So I get that N Cv delta T, this one here, is equal to N Cp delta T minus P delta V. Now let's use the ideal gas to rewrite this minus P delta V. So we know that PV is equal to nRT, and so we can write that delta PV, right, the change in this quantity PV is equal to delta of nRT, right? So then, and with that, then I can write that this is equal to P is constant, right here. This is a constant pressure process. Delta V is equal to nR delta T. This is true for a constant pressure process. So now I can put this back in here and I get that NCV delta T plus NCP delta T minus NR delta T uh, is equal, this is equal here, right? And then I can cancel the delta T's now and the number of moles, and I get that CV is equal to Cp minus R, or Cp is equal to Cv plus R.